In talking about hybrid rocket motors, we were talking about a fundamental process that involved the vaporization of the fuel with an oxidizer that's fed into a mixing region. So we may have a mixing region that looks like this, and within this mixing region is a combustion zone. And so we have the oxidizer coming in from the outside, and the fuel coming up in this direction, and then this is the flame zone. So now this has been the fundamental problem that we've been looking at. And the other day we went through and got several relationships for shear stress coefficients for flow over a surface and heat transfer coefficients. And we had, to summarize a little bit here, we had an expression for, this is actually the Colburn relationship, for the heat transfer coefficient on a surface, C sub h times Prandtl number to the 0.67 power is C sub f over 2. So CH is defined as the Stanton number. Originator. This, you could say this is the Colburn relationship, and CH is the Stanton number in that relationship. And CH is defined as H sub F over rho C sub P U bar. This was it within a smooth tube. And then for a flat plate, we have the relationship is similar in that, well, it's the same thing. H F over rho C sub P U sub infinity times the Prandtl number to the 2/3 as C sub F over 2. Okay, so now what is the physical meaning of this particular term? The Stanton number. The other day we talked about. Do you see how that comes out of there? If you had H sub F times a temperature difference, T wall, let's T sub infinity minus T wall as an example, over rho C sub P U sub infinity times T sub infinity minus T wall. This, just multiply and divide by that temperature difference. Then this numerator is what? What is the definition of HF? It's actually, the film coefficient is actually the heat transfer divided by the temperature difference. So this is the heat flux from the stream into the surface across the film coefficient. Now, what is C sub P times T sub infinity minus TW? That's an enthalpy difference. And rho U sub infinity, that's a mass flux. And so this looks like that this is a heat transfer into the surface. Now that would be the heat transfer into this surface. That would be Q surface. Right?
So is it negative? It's going into the surface? Is it hotter away from the wall than it is at the wall?
Uh-huh. Yeah, you've got this flame front out here.
Okay.
And so you've got a heat transfer from the flame front into the surface. And I've kind of here we could put this, since we're multiplying and dividing by the same thing, yeah, that's this relationship right here. These two things essentially cancel out. So what I'm looking for is just a physical description of what this Stanton number represents. So HF times some T plane front or T away from the surface minus the temperature at the surface represents the heat flux into the surface. And then rho C sub P times U sub infinity times the delta T represents an enthalpy flux. And that was the representation I wanted out of that ratio. So the Stanton number is like the Reynolds number. It's like the shear stress coefficient in representing this heat transfer term. Yes?
If I remember what some of the things I read, in solid rockets, it said that it spun the rocket further faster.
Uh-huh.
Would the same thing happen with a hybrid? Would it
Probably.
oxygenate to the
Probably, because of the forces applied to those gases. And if you have a liquefied metal, of course, and that keeps the hot liquid metal near the surface, or brings the burning liquid near the surface. So it diminishes that distance. Anytime you diminish the distance between the flame zone and the surface, you're going to increase the heat transfer. Ms. Greenlee. This is in a pipe flow. This is in a pipe flow, so this is a bulk velocity or a mean velocity across the pipe, the cross-sectional area of the pipe. Anything else on meaning of these terms? Okay, now let's turn to the hybrid analysis itself. Now, we'll take this first relationship that says the Stanton number is C sub F over 2 times the Prandtl number minus 2/3. And we'll also note, now, if HF T sub infinity minus T wall represents a heat flux, and this is equal to CH, so that we have CH now from this definition of the Stanton coefficient, or Stanton number, will be equal to a heat transfer rate into the surface. And I suppose we should put a dot on that to indicate a rate term. Now, where does that enthalpy, where does that energy go? Well, in the denominator, when we apply it to the flow in this boundary layer, we're going to talk about a rho sub E, a density at the edge of the boundary layer, times the velocity U sub E, times a delta H across this flame zone. So now delta H will be the enthalpy difference between the flame zone and the fuel surface. Any questions about that? Does that make sense? Ms. Greenlee, you got a question?
Yes, I was just wondering, could you indicate on your drawing where we're talking about here? The flame zone, meaning at the
That's
top
this.
edge of the flame zone?
No, that's in this region right here. And then this region is the fuel surface.
So is T infinity the flame temperature now?
In that equation it is. It could be, this since it's in numerator and denominator, this could be the flame temperature down here.
And that would have to be use of flame temperature as well. The U in the denominator there would have to refer to the flame as well, wouldn't it?
Yes, it would. But now we have to be careful. This term right here represents a mass flux. And it represents a mass flux into this boundary layer.
So the U sub E is going in our drawing is going vertically.
No, UCB is horizontal.
It's horizontal.
Uh-huh. So at any given instant, UCB is coming in, is the mass flux in this direction.
Oh, it's at that edge up there?
Uh-huh.
Okay.
Up here. So if you took rho sub E, U sub E times the cross-sectional area of the port, you would get the mass flow rate down through the center. Now, I don't want to be overwhelmed by the outburst here of understanding.
Lights are on and shining bright.
Okay, good.
Now this enthalpy, that's the enthalpy of what? Of the air or the mixture?
Of the gas.
Yeah.
Mhm. That's the enthalpy of the gas at this point, and the enthalpy of the gases at this point. Okay, now, any questions about that Q dot sub S? Well, Q dot sub S is what? What's the if you've got a heat transfer rate into the surface, what's the objective in the hybrid rocket? What do you have to accomplish? You have to vaporize the fuel. So we're going to have the density rate, the density of the fuel, times the regression rate, R, of the fuel surface, times the enthalpy of vaporization of the fuel. Ben?
Oh, I'm just trying to figure out what R is.
That's the rate of surface regression inches per second.
Okay.
Have we got it? Now, Q dot sub S is also equal to H.
Now the R, usually it's in inches per second, but when you use it.
Or
multiply on the
meters per second.
Change it to meters.
Yeah, when we put the numbers in, we'll change it to the units we need. Now, this H sub F, now the nomenclature really gets confusing. This is the heat transfer coefficient times the temperature difference across that region.
So it's not the enthalpy of
No,
the fuel.
no, it's not the enthalpy of the fuel. It's an enthalpy. Excuse me. It's a heat transfer coefficient.
So that's the film coefficient.
Yeah, that's the film coefficient. All right, now when you have heat transfer across the boundary layer by so-called convective means, where does that heat transfer go? Well, it goes into the surface, and so that goes into a heat transfer term that involves thermal conductivity times and this is of the gaseous phase, times the gradient in the temperature at the surface. Does that make sense?
K of G is the thermal conductivity of the gas at the surface.
Uh-huh. Now, the regression rate is given by,
This is R.
this is R, C sub F over 2, delta H over H sub V, rho sub E, U sub E, over rho sub F, Prandtl number to the minus 2/3 power. When you combine all those things together, you get this. That's the density of the fuel. That's the velocity U at the edge of the boundary layer. Did you see this on this schematic? Right there. And that's the density at that edge. Now, should I pick on one of you to give me a verbal description of what's in there? You're saying, not me.
So is R just all these leftover terms? Everything is left over, you stick it in R and call this the regression rate?
We need to know what the regression rate of the fuel will be in this rocket motor.
What is H sub V?
The enthalpy of vaporization, or sublimation, or transformation.
That's tabulated, right, the H sub V?
Hopefully.
Otherwise, it would be experimentally determined and plug a single value
That's right. You got it. You got it. Chad? Inches per second. We're gonna fix this up to match the unit. We'll fix it up to match the values too. Any questions? I'm looking along the back row there. So this first term right here, well, on the left, the regression rate is what? That's the rate at which the surface is gonna move, right? That's the rate at which we're gonna transform the fuel from the solid phase into the vapor phase. Okay, that's what we're after. Now the terms on the right, CF over 2 is what? I think, Dan, I asked you first. What is C sub F? Go ahead.
Is the regression rate gonna change as you go down?
Oh, you bet.
I figured it would.
It certainly would. The shear stress coefficient, does it change with length in a flat plate? If I have a flat plate and it's nice and laminar flow, now you folks are getting ready to graduate, you're all heat transfer experts, you know all about conduction and convection, all that kind of stuff. And you got a laminar flow here, C sub F over 2 is equal to how much? Well, C sub F over 2 from your notes. Well, what's the number? For laminar flow with air at room temperature, starting with the distance x and some velocity out here, u sub infinity, what is the shear stress coefficient for laminar flow? What did I call what? Shear stress coefficient.
Yeah, you're assuming that the Fresnel number there is gonna be 0.664.
No, this is just the result for laminar flow without property dependence on the Fresnel number. This is just an incompressible flow over a flat plate with x measured at the front moving downward, no pressure gradient. I mean, a uniform velocity on the outside. So in this expression, R E sub x is rho u sub infinity x over the viscosity. Okay? So given the temperature and the pressure and the velocity, the temperature and the pressure we can determine the density. The temperature we can determine the dynamic viscosity. So we calculate the Reynolds number and it's a function of distance x. You agree?
So does this, C sub F decreases with this?
Well, now C sub F is the shear stress coefficient. Does it increase? Does it stay the same? Or does it decrease as you go downstream?
Decreases parabolically.
Inverse to the square root of the distance. So the shear stress coefficient on a flat plate, this plate right here in front of us, decreases as you go down the plate by that rule. Anybody with me? Okay, so then what relationship does this have to this expression? Mr. Bird?
Burning rate's faster towards the left side of our drawing
Because?
because that the coefficient is lower as you go
As you go
right.
downstream, the
Downstream, you're farther away from the heat source.
possibly, you bet.
The flame is farther away from the fuel as you go down.
Well, now we're not talking about a Venturi effect. We're talking about as you move downstream, the velocity gradient changes, the shear stress acting at the surface changes. This says that the shear stress as you go downstream decreases by 1 over the square root of x. Well, if the shear stress decreases, what happens to the burning rate or the regression rate? It decreases because of that change in the shear stress coefficient. So that decreases the heat transfer rate. Okay, so now, did we get this point about, well, we're right here at C sub f over 2. What does C sub f over 2 have to do with this problem anyway? What was the term we introduced for that? Reynolds analogy. Reynolds analogy says that the heat transfer coefficient is a function of the shear stress coefficient. So this is related to the heat transfer coefficient, right? Through Reynolds analogy. You're all giving me these blank poker face looks like you've never heard of that before. You haven't? We did it a couple of days ago, I believe. One day? Do you want me to write it down?
Depends on the 48-hour day.
Okay, let's go to the next one. What is delta H? Mr. Bird.
Is that still, we ignored the mass injection?
No, we haven't yet. All I'm saying is this is CF0. This one is without mass injection. And the reason why I brought this up was to get the dependency on X. This one is the actual CF, and I'm going to have to introduce the mass injection in a moment. But I want you to get a physical feel for this before I go on. You with me? Okay, this delta H is what? Chad? It's the difference between the enthalpy at this point and this point, right? And the HV, Krista? Enthalpy of vaporization of the fuel stuff. Rho sub E, U sub E is what? That's the mass flux of the main flow stream. You see that? Rho sub F is, Mr. Franco? Rho sub F. That's the density of the fuel. Prandtl number, mu C sub P over K. So this is dependent on those properties. Mr. Green.
Is the velocity on the edge of the mantle layer, is that changing as we're going in the next?
We're assuming zero pressure gradient down the duct initially. But in fact, it will have a pressure gradient. But we're ignoring it for the moment. Okay, now we do have a problem here. We have to fix this up here. So we'll say experimentally, and it's also theoretically, but we'll use this expression. C sub f over C sub f0 is equal to 1.27 b to the minus 0.77. And there's a range on this for this b factor. And we'll put some definitions in here. C sub f0 is defined over 2, is defined as 0.0296 Reynolds number based on x to the minus 0.2, and this is for 5 times 10 to the 5th less than or equal to the Reynolds number, less than or equal to 1 times 10 to the 7th. So that gives you a range. And B is defined as rho V at the surface divided by rho E U sub E C sub F over 2. And this is given the name the surface injection parameter or mass transfer parameter. And it's also got the C sub F over 2 in it, so it's a It's an implicit embedded function.
Or the function depends on itself.
Yeah. Now for Prandtl number equal to 1, B, the blowing parameter, is related directly to the delta H over HV, where this is H of vaporization.
What is V in the B equation?
The vertical velocity.
So it's the y-dependent velocity?
Yes. At the surface. Let me put that down. And rho is the density. V is the vertical velocity at y equals 0. So it's the mass injection velocity. It's this velocity over here, V. Sometimes it's given the symbol VW. It's this vertical velocity at the surface due to the mass sublimation. Okay, let's go back up at the front here. C sub F is the actual shearing stress coefficient at the surface. C sub F0 is a non-blowing shear stress coefficient, empirical. Experimentally, it's been found that the shear stress at the surface is reduced by blowing or having mass transferred into the boundary layer at the surface, and this kind of an empirical function can describe that reduction in the shear stress coefficient. Now this is the way you cool off those rocket nozzle materials. This is the cooling effect in ablation. You see it?
Pretty big range on V. How do you know what to tip?
Well, you calculate that from this function. See, you know what the enthalpy drop is? Well, from the combustion process. You know what the enthalpy of vaporization of the fuel is, so you can estimate a B value. And then you can get an estimate, a preliminary estimate of these parameters, and then get an estimate of this. But this is an empirical relationship. Now, this one is the shear stress coefficient on what side, in what kind of flow. Notice that the exponent is different than the exponent we had on this fancy relationship we just erased. What's the difference between this one and the one we had written down with? This is a flat plate. This is turbulent flow. Look at the range of Reynolds numbers. And this exponent, the exponent indicates that's turbulent flow. Okay, so then, skipping a few steps, R becomes equal to 0. Wonderful. G to the 0.8 divided by rho sub F times mu over X to the 0.2 power times B to the 0.23 power. Now that's a more accurate relationship. Now G is equal to rho sub E, U sub E is the mainstream mass flux. Is anybody with me?
No,
Okay. All right, now there are several empirical relationships. Simply R equals A G to the N, where G is equal to rho U A, that's the cross-sectional area, divided by the area of the port, or M dot over area of the port.
Aren't we saying that's the same G
Right, that's the same expression. All of this material that we had here in defining the regression rate have been included in this expression. Okay, so now for this expression, we have a range from 0.05 inches per second, less than or equal to r, less than or equal to 0.2 inches per second. And we have a range on n from 0.4, less than n, less than 0.7. So for HTPB, which is a hydroxyl terminated polybutadiene, now, spell that really quick, Rick.
Say it now.
Say it fast, yeah. For a mechanical engineer, if you say that kind of thing, there's a cloud that comes across the eyeball, just almost immediate. Okay, for this kind of a fuel, this relationship is 0.104 G to the 0.681. Okay.
There's a decimal for that. 0 or put the 0 and 4 there on the second line.
Okay, any questions? Ask me some questions.
A here is same A as in you use the burning rate expression.
Let me write it over here. For solid propellant, R is A P sub C to the N. These are not the same values. The A's are different, the N's are different. Now, what is the difference now between this solid propellant and this hybrid? What is the governing parameter? Over here, the governing parameter is chamber pressure. You raise the pressure, you increase the burning rate of the solid. Right? Now over here, what is the governing parameter? G, which is the mass flux along the center port. I'll have to read it. Hydroxyl terminated polybutadiene. It's rubber. You know, when the rubber meets the road, that's the stuff. That's the fuel. Okay. G is Miss Bird.
Mainstream mass flux. Where is that happening?
That's down the center port. We're down the port.
So it's the oxidizer plus the vaporizer.
Whatever's mixed and burned.
And that changes with the sum of all that mass.
The sum of the mass.
What's coming out of the fuel and the oxidizer.
You got three components to G. You've got oxidizer. Okay. You have burned products of combustion, and unburned fuel. Now, the implications behind that are pretty severe. Because if you've got a long grain like this, you've got a port coming down. Here's your fuel, and your oxidizer is coming in. If you don't have enough oxidizer, by the time you get down to the end here, you're not burning up anything. I mean, you've just got a combustion product. So you have to have enough excess oxygen so that it gets to the end of the grain. Now, the implications are quite extensive. So one of the first things I'd like to do here is get a comparison between the hybrid burning rate and the solid rocket burning rate. Notice the difference in range, 0.05 inches per second. Now, I want to compare that with a solid rocket. Before we get that comparison, keep asking me some questions. Rick? Okay, Dave?
The area of the port is the instantaneous area at any location.
At that location, that's right. Yeah, so that would be the cross-sectional area of the center port, or the port through which the flow is passing. Ben?
Can you cheat on these hybrid rockets?
Cheat?
Yeah, and sneak.
Cheat is, there's no such word in solid rocketry as cheat.
Okay.
There are, the words that you want to remember are deflagration, which is a good thing, and detonation, which is a bad thing. You got those two words?
Yeah.
Now, you can fix this up so that you can get one or the other. If you cheat, you're going to get detonation. If you don't cheat and you do it right, you get deflagration, which is a nice normal burning rate. Now, Ben, which of those do you want?
Well, what I want to know is what would be the effect of sneaking a little bit of oxidizer into your fuel at the end of the grain?
Well, you'd have a nice long oxidizer pipe on the outside, right? Is that what you're talking about? And I'm sure that you can do that.
I'm talking about putting the oxidizer right into the fuel, like in the solid rocket, but only towards the end of the grain.
Oh, well, then you're going to mix, then you're going to have a mixture of hybrid and solid rocket. And that is what's being proposed.
But
Not just a pure, let me finish it. Not just pure fuel, but some kind of a solid rocket motor
with extra oxidizer.
with extra oxidizer. Then I put hydrogen out here. Then I bring hydrogen in as a fuel and let it mix with the extra oxygen and burn in that mode. So you see there's a whole range of creative solutions to this rocket motor problem. Are you with me?
Yeah, I am.
Okay, Ken?
Well, mixing the oxidizer with the fuel.
No, we're going to mix this as a regular solid rocket propellant, only it's rich in, say, oxygen. And then we'll put hydrogen out here and burn that in the boundary.
Ben was saying though that the burn rates are so much different.
Well, now you've got a mixture of that one and this one. That gets quite a bit more complex. What I want to look, anything else? Glenn? So what is the fundamental mechanism driving hybrid rocket motor surface regression rate? The mass flux into the center port. What's the fundamental mechanism in this solid rocket? Chamber pressure. Quite different mechanisms. In our text, we had a table of burning rates for solid rocket motors. We'll have to find that. Which page? Yes, page 267. Now, notice that what is the typical burning rate for a high burn rate composite? From 1 to 2 inches per second. The maximum that we get out of this one is 0.2 inches per second. Well, the burn rates are much lower in this case, and in that case, the burn rates would be much higher. So, you know, it's just obvious how you're going to mix hybrid with a mixed hybrid solid rocket grain configuration. And the typical burn rate for JPN type double base propellants, the typical burn rates are on the order of 0.6, 0.8 inches per second. Now, you'll notice that the burn rates in this one are from 0.05 to 0.2. So these are a factor of 10 lower than for a typical solid propellant rocket motor. Yes?
What would be the benefit of doing that, of mixing the hybrid with solid with the rocket? Putting the hydrogen down with the extra oxygen coming out of the...
You get an increase in specific impulse, an increase in theoretical performance. You also have a capability of throttling the hydrogen flow rates. So you could actually throttle the flow through the system.
Somewhat control how much thrust you're getting out of it.
Controllability, that's a major factor. No, because you'd have a mixture, you'd have a solid rocket that was going. Now, there are ways of turning off the combustion of the solid rocket, and that's by depressurization, where you open up the port on the chamber. The pressure drops and it pulls the combustion front away from the surface and extinguishes the combustion. The problem is that the insulation in the inside of the chamber and the solid propellant fuel itself have absorbed a lot of energy, and so they continue to vaporize and reignite the mixture. So starting and stopping solid propellants for controllability is a difficult thing, and so that gives you motivation for looking at configurations of hybrids that will that allow you that controllability.
Has it been done successfully in solid?
Pardon?
Has it been done successfully in solid?
I'm not aware of an operational system that's been successful controlling that. Now, there are ways of mixing the fuel grains. You can have a different fuel or solid rocket composition at one part of the trajectory as compared with another part. And so you have to cast them differently. Or you have to cast one type of propellant and then cast within that the other type of propellant. And that's been done successfully. Yes?
Has the hybrid rocket been used for anything that we know about, like putting a satellite up or
Not for anything like that. Now, the American Rocket Company is a commercial operation, a private company that are building these, and they had a system that they fired several months ago, which failed on the launch pad. But those are to be expected when you're developing advanced systems. But it's very expensive. Very expensive. Any questions about this? Do what? Well, no, that one fell over and burned.
If you ever see the movie with the right stuff that shows the progression of this,
Mhm.
it shows like I'm progress.
Well, the one I particularly enjoy is the movie taken in the bunkers on the German rocket development, where one film shows the V2 going up and then the other one shows it coming down right next door. It's just up and down, right out of the window of the cell block there, looking at the rocket. I thought that was a good sequence of pictures. Our schedule then, Monday we will review hybrids. Tuesday you'll be off to a party.
Of course,
That's always what you want to do in the spring.
No seminar.
Well, there is. It's over at Sunnyside Park.
It's not here.
Not here, no.
We're not taking roll.
And Wednesday, now look, I'd like to make this suggestion. Our final is Monday morning at 9:45. Oh, 10:15? I'm going to give you time to go from that room over to this room. 10:15, okay. 10:15 on Monday morning. Now, that means that I would like to make the review on Wednesday. And I haven't given you any homework on this. I might have you write up an outline of hybrids rather than extensive calculations. This could get very messy. Well, some people probably do, but but to avoid that, we'll make the final exam open book and open note. Now, if you take a look at this expression, immediately there's a question that comes up: what is the viscosity of the gas? Because you've got a mixture of fuel, an oxidizer, and combustion products. So that gets to be a problem. That gets to be a significant problem. What is the B value? We talked about that a little bit. So what I'm saying is I'm not going to give you a computational assignment on this, but I'm going to ask you some questions, a question or some questions on the final about hybrids. Okay, so our schedule is going to be as follows. Monday, we'll review solid rockets. Tuesday, you're off. Wednesday, we will review for the course. Now, here's the proposal is that we just not meet on Friday.
But if we turn in the homework just for chapter 11 on Monday,
On Wednesday. Everything on Wednesday. Well, these guys have called a holiday. you're not part of that.
Well, we are, but.
Oh, yeah, there'll be a school, but you got a departmental-wide picnic. When, Tuesday. So now let me state this again. All homework will be due on Wednesday. Whatever we've gotten assigned that you haven't handed in is due, 10 to 12, whatever is due. Say again? Everything is due by Wednesday. Any old computer programs that you haven't handed in, any homework that you haven't handed in, the latest we'll accept that is on Wednesday. Simply because the time frame is too short. Everybody clear? Any questions? I'll be available on Friday for any questions in my office. Yes.
What homework in the syllabus exactly is supposed to be assigned?
Now we dropped the material in chapter 12.
Yes.
Through chapter 10 and 11.1 and 11.3. Yeah, the rest are just dropped. So, and I have not included at all anything from chapter 12. Thank you very much. We'll see you on Monday.